All right. So hey guys. Today I'm trying to start off with a small lecture on linear algebra. And before I start, I should sort of give a word of warning, I guess. Everything that linear algebra is a big subject, and it's got tons of applications, and people like Strang are still you know doing stuff, and there's like new courses and books coming up and whatever. But what I am going to do today is a short recap of whatever we need to know from linear algebra, for the sake of Lie theory and Lie theory's applications to physics. So that's the talk today. And uh, I'm going to beg for your forgiveness in case I'm abusing any notation, especially if you're a mathematician. uh, Unfortunately, I'm in a profession called physics, and it's a day job, uh, in a sense. So anyways, we're just going to look at the basic ideas from linear algebra alongside some examples in physics. And I'm going to assume that you have seen special relativity in quantum mechanics in in some form or the other. You've read a little bit about it. So that will sort of help you through this lecture. And if you're a math major, don't even bother. You already know it. I'll see you in the next one. Um, so before I even get to vector spaces and all whatnot, I just want to clarify a bit of idea about sets and maps, because this will prove useful later on. So if I'm going to use this notation, pretty standard. A is an element of the set, big set A, and a one-to-one map is a map of this type. So if I have two maps that are equivalent but have different arguments, that just means their arguments are one and the same. So one element maps always to another one, and you can sort of visualize maps as the usual visualization is something along these lines. And onto basically means that every element in B is mapped to at least one element in A. And one-to-one means every one element in A is mapped exactly to one element in B. And we'll see what happens later on when we make use of both of these concepts. So let's dive into vector spaces. A vector space is essentially just a set V. So it's this set, and you have you have a set V, and you have two operations. So this is a vector space, and one is the multiplication operation, and the other is the addition operation. But the thing is, you have to define it over a field F, and not going to really go into what a field is, but for our cases, a field can be R or the field of the set of complex numbers C. All right. So the multiplication operation combines elements from R or C, basically elements from the field, and the elements in the vector space. The addition operation combines elements in the vector space with themselves. So they have a bunch of properties, and these are basically the axioms of a vector space. So you have a set with these operations defined over a field that follows all of these axioms. Then you can call it a vector space, and you can call its element a vector. So commutativity in addition and associativity in addition, and the additive identity, which is that there always exists this 1, 0 vector where you just add it and you just get the vector back again. And there's even a way to show that every vector space can only have exactly one identity as well. And every vector definitely has an quote-unquote inverse vector, or you can call it an anti-parallel vector or whatever. But essentially what happens is you just do the addition operation, you get 0. There's a multiplicative identity, and there's associative and distributive properties with respect to the scalars. So when I say scalars, I mean elements from F, and when I say vectors, I mean elements from the vector space. But again, the vector space itself is defined over the field. So these are the axioms, I'm gonna build some more constructs on top of this, and then I will walk you through some examples. But for now, trivially, you can say some examples are, R is Rn is a vector space. Uh, C is a vector space. Not sure if Cn, not sure if high dimensional. I'm not sure if that forms a vector space. And trivially, the other vector space that you can consider is the set of all invertible matrices with real or complex entries. So these are pretty trivial vector spaces. We don't really deal with them in physics per se, but they're pretty easy to sort of check these axioms out with and just sort of prove to yourselves that, hey, this is what a vector space is, and sort of have a picture of what the axioms are. The concepts that I'm going to build on top of this is span, basis, components, and linear independence. These are probably words you've heard somewhere. So I'm just going to sort of clarify what they mean or put it into words. So the span, let's say, we have a subset of a vector space, and if this subset, follows the same axioms and is defined over the same field, you can call it a subspace as well. So this subspace containing k vectors inside V, then you can say the span of V is essentially something called this guy. So what is this guy? So this is basically all the different sets of vectors I can get by adding them and sort of scaling them and adding them back again. Scaling them using scalars by multiplying a vector by a scalar and then adding them back again and combining them. So this is called the span, and this type of combination where I just multiply by a scalar and then add by another scale vector is called a linear combination. And we have a set of vectors in a vector space called B that are linearly independent. So what does the word linearly independent basically mean? It means that each of these vectors cannot be expressed as the sum of others, the sum or the scaled sum of others. So there is a neat way to show this using another construct, which I'll get to. But for now, you can the most simplest example is your ij, k, your Cartesian set, or your sort of this is just again linearly independent. And one way you can sort of show this is they are orthonormal. But orthonormality isn't orthonormal in the sense they are of unit length and perpendicular, mutually perpendicular. But I'll sort of show you later on that orthonormality isn't a prerequisite. It isn't necessary for things to be orthonormal to be bases. You can have non-orthonormal bases. But orthonormality is what you usually deal with because it's easy to deal with. So you have bases of unit 1, length 1, and then they're mutually perpendicular. And there's even a procedure to get from non-orthonormal to orthonormal bases. Maybe we'll discuss this during the Q&A. And we have a quantity called the dimension of a vector space. If you have a finite set, this basis set, if it's finite, then you can actually count the number of bases, and then you just call that number the number of bases or the basis vectors, the dimension of that vector space. And if it doesn't exist, you call it infinite dimensional. And it's pretty important, so we'll come back to this. And these scalars that we're sort of multiplying, so if I can express a vector psi as something like this, if this is my vector, and these coefficients are called its components, and in fact you can have a matrix representation of it. And mind you, this vector is independent of what basis you choose. I can define this in a different basis by transforming it using a transformation matrix, multiplying it, and it would just change me the components. The components would change, but the vector exists independently of the chosen basis. So that's an interesting idea. And also in physics, we usually use these kind of vectors because you can see that if you try to take the length of this, if you square the components and you add them, you end up with one. So these are quote-unquote normalized vectors. And you've probably seen these things in quantum mechanics. And now I'm just going to list out an example or two. So I did talk about set of all invertible matrices with either real or complex entries. And right from this, I can talk about the set of Hermitian matrices with real or complex entries. And I'll tell you why this is interesting. So first of all, what is a Hermitian matrix? A Hermitian matrix is simply a matrix of this form. What do I mean here? If I take this matrix, complex conjugate all of its entries, and transpose them, basically switch up the rows and columns, I get back the same matrix. And such matrices are called Hermitian, or sometimes they're called self-adjoint. So these self-adjoint or Hermitian matrices, I can denote this as this, and these do indeed form a vector space. But why do they interest physicists is, I hope I'm getting this this notation right, but usually when you're expressing angular momentum eigenstates, you get something of this form, this ylm theta. But the truth is, this ylm theta, these coefficients are basically just this space. It's a vector space. You can definitely form a vector space out of it, and out of these matrices. And we'll see later on in another lecture, in the next one actually, that you can then even talk about this in tensorial terms. But essentially, it's just this guy. And another vector space that we can talk about is this guy. Let me just write it out. Whoops. And yeah. So L or A or whatever here, but essentially this is just the Fourier transform. And in fact, whenever you Fourier transform, you're basically going from one vector space to another vector space where, or you're changing bases in a sense. You're changing bases to this basis, and these are the coefficients. And these Fourier coefficients have this 1 by 2 pi is, the integral cosine whatever form, and these bases are your trig functions. This is basically just cos theta plus sin theta at the end of the day of this factor, and this L is just weighting, is just a weighting factor. And so when you transform things, you just go to a different basis where, and that's kind of why we use integral transforms in physics in the first place, because sometimes your PDEs or ODEs may not be solvable in the space you're talking about them. So you just make a change of basis, you go to a different basis, and things probably are easier, more computable there. And definitely the set of all Fourier transforms, these do form a basis. These do form a vector space. And another interesting vector space is the set of all square integrable functions. So when I use L square, L square definitely has a different interpretation in math. L square in general can be used to talk about functions in general, spaces of functions where each vector is actually a function. But here I'm strictly talking about functions of this form. Let me write it out. The absolute square converges. So every function whose absolute square converges, those functions are termed square integrable, and you have probably seen this form in quantum mechanics, and it's one of the defining characteristics that the vector space in quantum mechanics, the Hilbert space, we always assume this to be true. But the Hilbert space is it's just in a sense a restriction of this, and in fact this you needn't even talk about this bound here. You can talk about L square of R, where your boundary can be infinity itself. But this is usually used to refer to particles whose potential shoot up to infinity, like your square will at certain sections. Um, uh, and for a free particle, you definitely need to consider infinity as bounds in the integral. Yes. So, so as I was just saying, so with functions you can form a vector space, but there are very special types of functions that we will be dealing with, and these functions are maps, or these transformations are called linear maps, and they have these two properties that when I take the sum of two vectors as the argument, it's just equivalent to taking each of the arguments separately and adding them both together. And when I scale a vector and I put it as the argument, it's equal to scaling the entire result itself. And wait a second, yeah. You can definitely consider the set of all linear maps over a vector space, and that does form a vector space itself. And I think the right word is if you have a linear map of the form that maps from V to V, I think it's called an automorphism. But leaving this aside, this is not really important. One interesting representation that we will use on later is, let's say that with these maps can be represented by matrices, real complex entries. Now the thing is, from this, you can actually create a different representation of it called the adjoint representation. I'm not going to go into details here about this, but I promise you this will be useful later. But essentially, the adjoint representation, or the notation I'll use here is AD of, with respect to a vector, with respect to a transformation A of another transformation B, is simply the commutator. And this adjoint representation, if you want a naive example, is arguably most explicit in quantum mechanics, where in the Heisenberg picture especially, where you have something of this form. Adjoint with respect to the Hamiltonian of B plus dou B by dou T. But it does have some niche stuff with respect to group theory that we will come to it later. But I just wanted to sort of point this out, that you can have this sort of adjoint representation. Okay. Now, gonna build another construct on top of this, and it's called a dual space. I'm gonna denote it with V star. And all it says is that, one second, there exists an element of the dual space, and every element of the dual space is essentially every element is a linear map, and or a linear functional, because it's a function that takes something out of the vector space to the underlying field. And it, again, here it doesn't need to necessarily be R. It can be the field, and the field can be C or R, or whatever construct. And again, the idea, the mathematical object field has its own set of axioms, It's and again there are some troubles when you talk about C as a field, but this is just an object, and for our purposes, it's either R or C. All right. So this is a linear map that takes a vector. This is a linear map that takes the vector to its underlying field. That's all it does. That's all the dual space does. And very much like the vector space, you can assign the dual space a basis set, EI. Just want to emphasize this a little bit because it's going to pay off later on. Usually when you're denoting the dual basis or the set of or the basis set in the dual space, you usually use upstairs indices. Whereas if you look here, we were always using downstairs indices in this case. This isn't really something fundamental, but it's more of a convention that the basis must have, if you have a basis W, let's say, I can express W as some alpha E1, alpha 1 E1 plus alpha 2 E2. This is how you would represent the dual, and the representation of a vector is the opposite in terms of indices. Oops. So yeah, again, this isn't found in math. From what I've seen, there are different conventions, but usually in physics, when you're talking about duals and vectors, and you want to expand them with their components and their bases and so on, this is the convention that's followed. This is how we sort of label indices. And it's kind of common to set up the basis in a way that if I take the basis, if the dual basis acts on the basis vector, then you get the Kronecker delta. Again, this is a convention to make things simpler. This doesn't have to be the case, but most of the time this is taken to be the case because it just makes things simpler, just makes life easier. You can have a different, crazier basis, like I said before. You do not need them to be orthonormal. And let me maybe just write the word out. Ortho means they are perpendicular, which I will define to you in a second. Normal basically means length. It doesn't have to be this way, but we just take it to be that way so that life is easier. And this sort of brings us, this idea of duals brings us to this idea of non-degenerate, long words ahead, really long word, non-degenerate Hermitian form on a vector space. So these are all duals. Every vector space definitely has a dual, but this is a construct that I'm building on top of a vector space. So not every vector space has a Hermitian form. All right, and sometimes it may not even be possible to have a Hermitian form for every vector space. It might be a different form for all I know. But in physics, we are mostly concerned with Hermitian forms of the non-degenerate type. And again, it's just a function that takes two vectors, and in a sense, it's called a two form. So all it does is it takes two vectors and it assigns a scalar from the field. So it is similar to the dual, but the dual was mapping from V to F. So this is the dual's definition, but the definition of a form or of a two form in this case is that it takes two arguments and it gives me a part of the field, and it takes an ordered pair and it gives me a scalar. And this ordered pair idea does run into sort of conflict when you're considering just C1 or the complex plane, but we will not deal with that Thankfully, that doesn't pop up anywhere in what we're going to be doing. But please be aware that it's darning to do that. And maybe I should have struck this off. But just it takes a pair or not pair, and you have this notation, and it has a bunch of properties, and it's linear for vectors. Okay, so you can do your usual scalar product and your vector addition, and then you would get linearity. It's very similar to the linear maps. And you have hermicity, which is to say you flip the arguments, you have to complex conjugate the result to. So to obtain what was unflipped beforehand. But this skew symmetry only holds if your scalar is C. This would just turn into symmetry if your scalar was R, because you complex conjugate a real number, you just get a real number back again. And there's this whole idea of non-degeneracy, and there's the idea of positive definiteness, where unless you have a zero vector in the form, you always end up with a number that's larger than zero. So we've sort of considered, and there's one more idea, which I will sketch out, but we've sort of considered all of, like, too many ideas, I should say. And in a slide or two, I will sketch out what they mean in the context of special relativity and QM, and then maybe we'll close for questions. But essentially, there's a link between these non-degenerate Hermitian forms, and when I say form, I mean certainly non-degenerate Hermitian form. It's a long word, and that's why I'm not saying it again and again. But there's, in a sense, this guy can be represented as something like this. Oops, I should probably do something like this. Yeah. Why am I writing it this way? And what I mean here is there's basically a symmetric bilinear. I'll get to this. It's a function basically that takes a vector and spits out its corresponding dual. So just like every vector space has a corresponding dual space, every vector definitely has a corresponding dual element, and this map that takes it, this map is, in the physics lingo, it's called the metric, although generally metric means your distance function, but you can use this to define distance, as we'll see in a second. And this dual that corresponds to a vector is called the metric dual, or simply the dual vector of that vector. All right. So when you see that it sort of flips the vector to the dual, you can then tell me, okay, that it actually makes sense. Why I wrote g of v vector here, because it's giving me the dual v here, and then I can just use the dual, and I can say that, oh, the dual acts on the w, and that definitely takes them to the field F. Why do I care about this is a very good question, and I'll probably start with simple examples and I slowly build it up. What is the form? What is the Hermitian, or just the form for my set of all invertible matrices containing real or complex numbers? So obviously there are a lot of them, but the most naive one that I am going to consider is the trace functional. So this is definitely a form, takes any number of arguments and then just gives me back my field, scalar from the field. But this is a trivial example, but what does it mean in the context of quantum mechanics and special relativity? So first and foremost, in the quantum mechanical set of things, my vector space V is actually something called a Hilbert space. So Hilbert space has two defining characteristics. In Hilbert space, the length of a vector v is defined as the square root of the form taken over itself. And without the square root, this is usually termed the norm. And this is how you calculate lengths of vectors, and these lengths actually correspond to probabilities and so on in the quantum mechanical concept. In special relativity, your four vectors or events form the vector space. They are elements. What am I writing? Events. They form the vector space, and you do have a non-degenerate Hermitian form, and it's often denoted as follows: x mu, x mu. And all that's happening here is I'm taking a two vectors, and I'm trying to compute the invariant space-time interval here. And why do I care? Because it's invariant between frames, and that's the reason I'm setting up this form on top of the vector space in the first place. And you have this neat relationship. It says x mu beta x mu x mu. So all that is saying is I can get you back your dual by just acting upon with a particular transformation. And this is the metric, and the metric, for special relativity, you have two equivalent metrics. So you have -1, 1, 1. I'm not writing the zeros, but this is just a diagonal. And the other way to write this is also 1, -1, -1, -1. Both give you the same results. This guy is the same. But the book I'm using chose the notoriously weird notation of 1, 1, 1, -1. They sort of shove time to be the last guy for some reason, even though in most cases time is considered the first guy. But these two are pretty much the same. Your ordering of components is different. And I might switch back and forth between these two, or sometimes even between these three. But you should know that they're all the same later on when we're trying to do stuff. And just for the sake of completing things, I should say that the second defining property of the Hilbert space is also the fact that all of the functions are, if you define a function over Hilbert space, all of these maps are square integrable. And a way of saying this is to say that they are complete. I'm not gonna delve into what this is because it would go into sequence and series, and I really don't know much about it. But all completeness means is you have a sequence of a type that you take the distance between one term and another term in a sequence, but the distance between the two successive terms keeps decreasing, and that sort of a sequence is called a Cauchy sequence. Complete basically means all sorts of those sequences converge. They always are less than infinity. They don't blow up, or they don't oscillate widely. So yes, I will stop here and we can dive into questions.